Hi, I'm Ronny Moe, and I'm here with Eirik Engen to present the project Drones in Rescue Operations in the subject Hardness of Sensors in Process Measurement.
Hey, this is Eirik Engen speaking. The conceptual design of the drone rescue system is based on a drone equipped with navigation sensors and optical sensors, where we feed the soft sensor module with navigation data and the laser rangefinder data that measures distance from the drone to an object, thermal camera image, and daylight camera image. So the soft sensor design of the automatic person detection was done using MATLAB and Python. I'm going to talk a little bit about the work we did in MATLAB. So you have the illustration of detection shown here on the two images, an RGB image and an infrared image, where you have a detection of a person. Uh, all traditional object detectors using three phases, where the first phase is you define a region of interest. You select this. This can also be done automatically as for the faster RCNN detector, or you can define fixed regions using anchors. Um, the next phase is the feature extraction, and the third is the classification of the object in each region using the feature extraction. Our down selection of detectors that we would like to investigate was the single shot multibox detector, which was selected based on its speed and accuracy and memory use. And the faster RCNN detector was selected based on its accuracy. To have an object or a person detection on a thermal camera, you need a data set that to base the training on. Um, there exists a lot of CNNs that are trained on RGB images, but not so many CNNs that are trained on thermal images. And it's a little bit more tricky to um, classify objects using thermal image because it has less information. Um, we found a data set of images from FLIR that is actually made for advanced driving assistance systems, and where you have a lot of data recorded from a vehicle driving around. And you see an example of an image set below here, where you have the daylight image, the thermal image, where you also have annotation of the objects in the thermal image, a car and some persons. The data set was used to train the CNNs used as basis for the SSD and the faster RCNN detector. So we extracted all the label box images from the training data set from FLIR. So it was more than 20,000 images of persons. So you see 30 or something of the persons on the right side here. So we trained the ResNet 50 CNN and MobileNet version 2 CNN with those data. So the investigation of the neural networks, we did that to find a proper feature extraction layer that we could select based on the features that we saw in the different layers from the neural network. So on the left side here we see the input images on the left, and the strongest activation channel from layer 1, the convolution after the first convolution. So they are a little bit different compared to each other, the infrared and the RGB. It has little different edge detection. So, and on the right side, you see the maximum activation channel of each layer on the ResNet 50 that we used for the faster RCNN detector. And we selected the layer 55 here, where you can clearly see the person as a white dot. This is the activation 15 ReLU layer. So for the faster RCNN detector, we based the detector on MATLAB example, where we replaced the CNN with our own retrained ResNet 50 CNN, and we selected our own extraction feature extraction layer. And for the single shot multibox detector, we did almost the same thing. We created using the example in MATLAB, and selected our own retrained MobileNet version 2 network, and selected our own feature extraction layer here as well. So due to some problems with training the SSD and faster RCNN network that we made in MATLAB, we tested using a different kind of detector. We trained an ACF detector, and the ACF stands for Aggregated Channel Feature. We tested it on both RGB image and infrared image. And the RGB image detected and classified the person with a confidence of more than 80%. And on the infrared image, we had to do a detection on the complementary part of the infrared image. And we had a classification with more than 50% confidence.
Okay, over to training of detectors with TensorFlow on the Google AI platform. We actually tried training the detectors with TensorFlow both locally and on the cloud platform. But the local training was hard to get working because of problems with object detection training on newer versions of TensorFlow. But this was solved using the Google AI platform, where you could train it on the TensorFlow runtime 1.15, and that worked quite well. Before training, we had to prepare the data sets, labeling images, and pinpointing the detector boxes. And for that, we used label image, and we created TensorFlow records of training and test sets locally before utilizing Google Cloud Jobs to retrain a single shot detector MobileNet version 2 model, and this gave quite good results. We managed to get the precision quite high, and the precision of the detector boxes, and also the classification. and we trained this model for 200,000 steps actually. The downside to this was, even though the model was quite precise in the evaluation, we weren't able to get the converted model. You have to convert the model to a TensorFlow Lite model to run it on the Raspberry Pi, and that wasn't working very well. And also another downside is that training on the Google platform can be quite pricey for personal training. But as you can see, the predictions that this model does is quite good. We get quite high classification accuracy, and the detector boxes are quite good. For the soft sensor design, we tried creating fused video for the Raspberry Pi. What we do here is that we fuse the images coming from the visual light sensor and the thermal imaging sensor. And the way we do it is that we has overlaid the images, and the intensity of the thermal sensor is determined by the intensity of the visual light sensor, so that in low light conditions the thermal sensor outputs a lot higher intensity. You can see that demonstrated here for a daylight camera. The intensity of the thermal image is overlaid. You can see the rectangular shape, which is the output from the thermal sensor, but it doesn't contribute much to the image. But in low light conditions, the thermal sensor is more intense. We also implemented a hotspot detection, which should detect the hottest area in the thermal image and output the position of that in the image. The way we do that is that we smooth out the noise in the thermal image by using Gaussian blur, and then we output the location of the highest intensity pixel in that smoothed image. We got the Raspberry Pi to indicate this location in real time using the OpenCV library. And you can see here that the hotspot is following the person in the image. We also thought of a concept of a situational awareness map that could be output to the operator, where the operator can get an overview of an area with needed information and points of interest in that image. And then the images should be both for visual light and thermal image overview. And this would be possible to enhance by stitching together several images and to create a larger overview of an area. And then we could use, for example, GPS coordinates to pinpoint where the images should be placed in this map. And then we move over to the implementation of the solution. We have a Raspberry Pi, which is connected to a Pi camera version 2 module via ribbon cable, and via USB we are connected to a Pure Thermal Mini with a FLIR Lepton 3 camera module for thermal imaging, and these are held in place in the same camera casing that we have custom designed and 3D printed. And for the software side of the implementation, we have a Raspberry Pi running Raspbian Buster with Python version 3.7.3. And we also run OpenCV library on this and Immutils. This is for processing the images from the camera sensors and also altering the images with Python. And to run a web server on the Raspberry Pi to output the images to a web browser, we use the Flask library. For the object detection, we use TensorFlow version 2.1. When working on implementing this, we've used Visual Studio Code with Secure Shell for remote debugging, which has worked quite well. The networks that we have tested on the Raspberry Pi is the SSD MobileNet version 1 quantized. This model can process images as fast as about 2 to 2.5 image per second, and it works okay up to about 50 meters distance. We get similar okay results from the SSD MobileNet version 3 small edition, but this is a little faster, so you get about 3 to 3.5 image per second. There are not that large difference between the detection precision between the models in our test environment. We have also been able to detect persons in low light conditions using the thermal camera, but this is only small distances, maybe up to about 10 meters distance to the object. In conclusion, we can say that the retrained networks for thermal image detection did not provide very good results. And also retrained networks for visual light detection of persons need some more study to get them working on the Raspberry Pi. And we soon saw that the scope of work covered by the automatic person detection was underestimated, which led to other parts of the project receiving less attention. Our experience is that object detection training and implementation is not a simple task. All in all, this project has been a great learning experience, and the topic of object detection and the other topics that we've covered in this project is very interesting. Thank you for your attention.